So beginning our discussion, our lecture on chapter 8. Our cover image shows CO2 levels over the history of the last 800,000 years, with the current dramatic change from, starting in probably the 20th century, and then what looks like a vertical line because of the large time scale, and it's shooting up to unprecedented levels of CO2 measured in parts per million. So, although there has been a fluctuation, which appears to have a pattern to it, a periodicity, nothing compares to the current change brought about by humans. And there'd be no other good theory to support the current change. Um, it's plainly put. So, key characteristics of the Earth, right? We like to talk about the characteristics of the planets. So, here we have it, right? Size, 1 and 1. Okay. Well, what if we wanted to express those in base units? Well, we absolutely could. In fact, as a rough estimate, the mass of Earth is 5.7 times 10 to the 24 kilograms. The only reason that we are calling it a unit of 1 is for the purpose of comparing between planets within the solar system. So if we refer to, Earth masses, it's a convenient way to compare planets. We can then say how much more massive Jupiter is as a multiple of Earth's mass, or how similar Venus is compared to Earth's mass, and so on. Same for radius, and also same opportunity to convert to base units, which is 6,370 kilometers, which are not in meters, but you could easily convert them to meters by multiplying by 1,000. So these are your values in metric base units. Well, of course, kilometers are not a base unit. Even though, right, K and K, you might think they both are, but kilograms are, kilometers are not. But if we wanted to convert this over, it would be 6.37 times 10 to the 6. So maybe 6.37 million meters. Radius, of course, is the distance from the surface to the center. The diameter is twice that. The density of Earth is 5.51 grams per cubic centimeter. If you remember our discussion of densities, and what kind of values we saw for dwarf planets, for how that compared to the low density Jovian planets, which we didn't see a number for in the last slide, but we just kept referring to as lower, or even how this number compares to the density that we briefly saw for Mercury for the sake of comparison. Well, this one's bigger than all of them. So Earth is the densest planet in the solar system. That's surprising because it might be expected that it would be Mercury, because Mercury is often described as sort of a stripped down planet due to its proximity to the sun. In other words, its upper layers have been blasted away due to the solar radiation that bombards it on a daily basis, But despite that, Earth is denser. The reasons are probably myriad and complex. There's not one good, clear explanation. There's no direct tie-in potentially with that high density and any life-giving properties of Earth or any of its other unique aspects, although it may contribute to its strong magnetic field. Probably just picked up some particularly dense composites. Maybe some particularly dense planetismals happened to be involved in its early formation. Maybe because of the formation of the moon and so much of the upper layers of the Earth going to form the moon, it left the Earth with more of its core proportionally, and therefore a denser planet. That, by the way, is a reference to the best current theory of how the moon was formed, which was from a massive collision shortly after kind of Earth was finished forming, and the huge portion of the Earth then becoming the moon. That would help explain the moon's unusually large size, as you saw in the quiz, right? Because it's one of a standout characteristic. The orbital period, 365.2 days. Okay, approximately, right? Because we know it's a little bit more than 365. This semi-major axis, also base unit, well, the opposite of, but comparative unit of the astronomical unit. That way we can compare between planets. Since I gave you the other values, I will do the same here and point out that an astronomical unit is 1.49 times 10 to the 6 kilometers. So it's 149 million kilometers, or 1.49 times 10 to the 9 meters. So 9. The rotation period, 1 day. We know that's exactly a solar day, which is 4 minutes longer than a sidereal day. So that's what we define as a day. I pause because if we're going to talk about characteristics and compare between planets, it makes sense to define a day, and which would be the solar day by definition, if you're not told otherwise. Um, but of course, the sidereal day is more unique to the planet because the solar day only makes sense in the context of the orbit. If it wasn't for our orbit, we wouldn't have to even define a solar day, right? If our planet was just spinning by itself and was one of these things called an orphan planet, which are thought to exist and not orbit any star, then we just, spin independently. In that case, it'd be the sidereal day. But that would be weird, right? Our axotilt, 23.5 degrees. The reason for the seasons. Differentiation. Okay. We know about differentiation, that it's going to exist in all spherical bodies. It's one of the key things that separates a dwarf planet from an asteroid. And we certainly have it here on Earth. During planet formation, the Earth formed out of planetesimals, that accretion of planetesimals, them coming together. This created a hot ball of molten rock because of the huge amount of energy that would be released due to the planetesimals coming together. I will briefly describe a picture for you that I described in the other section of a planetesimal collision, because I want us to at least consider that not all planetesimals that collided would have been like billiard balls, smacking into each other, although particularly brittle ones that then have the ability to melt once they crack apart. But instead, often would end up in some sort of orbit, but an orbit that was too close to be stable with too much tidal friction. And so what I want you to imagine is two, say, moon-sized planetesimals or bigger that are orbiting each other, but only a few diameters apart from each other. So drastically close. Because remember, for example, the moon is 60 Earth radii away from our surface. So imagine, a bigger object, but 10 times closer. Under those conditions, the tidal forces would be so large that they would cause the surface and a good section of the mantle, so beneath the crust, right, the crust being the surface, to be completely molten, even if they weren't already. Then there would be an exchange of rocks and rapidly cooling magma between the two worlds. So imagine these two worlds orbiting each other with a trail of matter, tying them from one to the other. And one of them, the smaller, gradually just falling apart, being ripped apart and settling its its entire mass onto the other planet, which would sink in and contribute all of that energy that came about because of friction. That would be a common type of quote unquote collision between planetesimals, where the whole process would take anywhere from tens of thousands to hundreds of thousands of years. Okay, so that made the whole place hot enough to have separational layers. And to get back onto the topic at hand. Okay, and as we know, the deeper layers are the more dense. Well, let's talk about earthquakes. We've got these layers, and turns out that with the differentiated layers, the seismic waves, which are the waves associated with earthquakes, travel through those different layers according to different physical principles. And that's mainly because of the two types of waves that are created from an earthquake. An earthquake is just some rupture in a solid. So you could have the same principles of earthquakes occur in a building, right? That suddenly has a crack form within a wall. And when you have some sort of solid and there's this sudden deformation within it, the energy that gets released travels in two different ways. And those are basically the two types of waves that exist in physics and the physical sciences. And those are longitudinal and transverse. But in the context of earthquakes, we give them special names. We call them S waves and P waves. Okay? And to match up which is which with the terminology that I just used, S waves are transverse, which simply means that the displacement of the wave is perpendicular to the direction of motion of the wave. So we see that this would be like if you took a rope or a slinky, using the slinky because it can display both types of waves, but whatever easily bendable long object, and you suddenly make an up and down motion and let that wave transmit down the object, then that is a transverse wave because up and down is perpendicular to forward. So the velocity, you could say, is horizontal, but the displacements are vertical. So that's a transverse wave. Transverse waves travel slowly in solids because they require the actual shearing of sections of the solids. Different solids can permit this type of wave a different amount. So if you get right down to actual engineering or material science, you would my statement about saying that a crack in a building is just like a crack in the Earth's mantle, or rather Earth's crust, could certainly be challenged because different materials are going to work differently, because they all have slightly different properties, different structures if you zoom in on the molecular level. But basically, any solid is able to wiggle in this way. It's able to, deform perpendicular. So you actually have kind of pieces of it shearing apart and then transmitting the energy along a path. But you know what can't transmit a transverse wave is a liquid or a gas. Basically anything that's not a solid simply cannot transmit transverse waves because there's none of that property to bring something back down in the same way. Now, you might think that, well, hold on, this transverse wave looks a lot like a wave in an ocean. Isn't the ocean a liquid? Yes. But when a transverse wave travels across the ocean, that's a special case because it's a surface wave. And it is true that you can have the equivalent of S waves, collectively known as transverse waves, travel across the surface of a liquid, where that liquid meets either another liquid, if you have some multiple layered system, like two liquids that don't mix, like oil and water, or as we know it best, where the liquid meets the gas of the atmosphere. But you would never have this type of wave traveling under the surface. The only type of wave that can travel through deep water independent of the surface is a longitudinal wave. And this is also the only type of wave that can travel through a gas. And a longitudinal wave means that the displacement of the wave is parallel to the direction of the wave motion. So we still have the wave velocity, the little V arrow, moving horizontally, but now the displacement is shown as regions of compact springs in this case, or coils of the slinky, and regions of stretched out, less compact slinky rings. And that's what serves the same role as, say, like the peak and the trough of the transverse wave. So here, displacement was bending something away from being just flat. Here, displacement represents either compaction or rarefication. So either, compression or stretching. They use a bunch of, synonym words. By the way, in both figures, this A is labeled. The A represents the amplitude. The amplitude is always half the distance between maximum displacements. So you can see that the amplitude for the transverse wave is just half the way from the peak to the bottom of the trough, right? Which trough is just a negative peak, where negatively measured relative to the horizontal midline. And then here, the concept of amplitude for the longitudinal wave is just halfway between the two regions of maximum compression, where the slinky is most compact. Now, the name, when we talk about earthquakes, is P wave. So just probably for historical reasons, earthquakes have these special names given to the two types of waves, even though they absolutely are just, examples of transverse and longitudinal, but they're called S waves and P waves. And the P waves are able to travel through a liquid. So that's the key reason that we're talking about this in the context of differentiation, because certain layers are going to be liquids and other layers won't be. And the P waves can travel through those liquid layers. The S waves simply can't. In other words, the S waves will be reflected off of the point where a solid layer of the Earth's interior meets a liquid layer. The P waves will just transmit right through that change from solid to liquid. Additionally, they travel faster, the P waves. So when you talk about earthquakes, the P waves are the ones that will reach you first. When it comes right down to experiencing earthquakes, there are a bit kind of some differences, but they become a little muddy and are beyond the context of the class. But generally speaking, S waves are more destructive and are going to be the stronger ones. If my voice starts cutting out or there's any issues with the video, please let me know. I got a warning that my internet was unstable. Hopefully it will not be an issue, but I'll check the chat occasionally. Okay, so this figure, which looks like it's something that I would have drawn, right, with writing on the slides, shows seismic waves and a map of them throughout the interior of the planet Earth. And we see the S waves shown as this sine wave looking form, right? Just as you might expect from what we were just talking about. The P waves are just drawn as a straight line. It would be, if we wanted to represent them some other way, it might be a dashed line with varying dashes, but it's kind of hard to show clearly. So we'll just use a straight line. I think it gets the idea across. At least separates the two types. Okay, these are the only two types of waves that are going to be traveling. And if we imagine some event, an earthquake event, happening right at this location, as shown, this earthquake is happening near the surface. Can earthquakes happen deep in the interior? Sure. But due to the way that we have our are tectonic plates, these concepts of ocean plates and continental plates and the way they move. We end up with a lot of earthquakes near the surface. So in that layer known as the crust. So after that earthquake event happens, the energy of the earthquake is transmitted by the two wave types. Because that is what's happening. This is about energy transmission. And we see that they bend at different rates. So they have different angles of refraction. And that we can kind of see that showing up if we say like follow the S wave and the P wave that stay closest to the surface. But even more important, if we follow the next closest pair of P waves and S waves, which we could always imagine starting side by side. So they're always going to start side by side if we zoom in enough, because after all, they're all starting from the same point source, at least, just a single point on the scale of the Earth. Well, when the two waves have reached the interface between the mantle and the outer core, we see the P wave transmits through the outer core, but the S wave does not. This causes basically a shadow effect of the S waves. They just don't make it through this whole region that's behind the outer core. And because of the change and the refraction that occurs because of the change, there's further bending of the P waves, which also causes the waves to end up at a particular location on the far side of the planet that obviously isn't a straight line path. Okay, if you drew a straight line from the earthquake location to, the other side of the Earth and had it say pass right through the center, well, other than the ability of a wave to pass directly through the center, because there is one that can do that, it at any angle they don't. And so we end up with a complete shadow zone with no S waves at all and very weak P waves, and then a whole region where there are some P waves that are more directly across from the core of the Earth. So this trend, this map, it's worth knowing because it is a good demonstration of the different wave types. But that kind of takes our focus to maybe the physics of the wave types and less to the interest, the planetary science of Earth. By the way, that's kind of what this subfield of astronomy would be called if you're talking about details of individual planets. Of course, it crosses the line into geology pretty easily, or even seismology. But if you wanted to compare to other worlds, comes planetary science. Okay, well, the purpose of all this and what scientists can do by carefully mapping and measuring timing and strength of all these different locations and which waves arrive there, and knowing the location of the earthquake that caused the wave in the first place, well, this is how we're able to really have a confident view of what the interior of the Earth looks like. It's not just guesswork, but it's actually careful measurement of waves over and over again with incredible amounts of repetition and detailed arrays of detectors that allow us to have a good idea about how thick the outer core is, what how thick the inner core is, and how thick the mantle is. Okay, so the waves let us map it. Okay, so I tried not to completely give this away. If the pink S wave cannot travel through liquid, the outer core must be what? Based on the figure. Ah, I got an answer coming in. Okay. Nick's not sure based on the question mark, but he's like, maybe solid. So we know that the pink S waves cannot travel through liquid. And what do we see? What does the figure show? Well, I'm glad I didn't give it away. So I made sure not to say what it was. Okay. So we got two more votes for the outer core being a solid. Okay. So do you see any pink waves going through that region, that yellow region? Because it's sort of like the orange, the yellow, and the gray. Are any of the pink waves actually going through the outer core? Thank you, Patrice. No, they're not. Only the P waves are going through the outer core. So that suggests that the answer is two. Because if there's no S waves, there's a reason for it, right? That's because they can't travel through a liquid. I mean, if you look at this one right here, there's that pink S wave with its kind of sine wave shape, and it hits that barrier between the mantle and the outer core, and it just stops. So that one is the most clear evidence that we're hitting a liquid. We're hitting a point where the S waves cannot travel through it. They will not be transmitted through a liquid. Therefore, the outer core must be a liquid. Okay? So the outer core is a liquid. Only P waves can travel through it. So we're moments away from taking our break. I guess I'll just point out that the outer core is a liquid. The mantle's a solid for the most part. It kind of becomes more liquid-like as you get um, down. And obviously there's big regions of magma. I mean, the crust, kind of floats. So the mantle's a little more complicated, but the vast majority of it is a solid. And that's what we're seeing here. Okay. So as a good approximation, treat it as a solid. Just remember that the tectonic plates are able to slide across it. So obviously it has some sort of essentially lubrication at the top of it, which is that it does have a liquid near the top and also some changing properties as we get deep. But that whole idea, getting deeper and deeper into the planet, well, you're getting to a point where the Earth, the interior becomes hotter and hotter. The interior of the Earth becomes hotter and hotter as you go deeper. And that's what leads to the outer core becoming a liquid. It's deep enough that the rock is at the surrounding temperature of the rock is above its melting point. So it's all melted and kept in a liquid state due to temperature. Interestingly, the inner core is a solid. And the inner core is a solid because of the high pressure. So you can think of it as this battle between high temperature and high pressure. The high temperature causes the phase change from the mantle to the outer core, which is what separates the two and why they're named separately from solid to liquid. But then as we go deeper and deeper down, the pressure ends up winning out and overcoming the effects of the high temperature. And that very high pressure compacts the rock back into a solid state. All right. So a state that is incredibly hot and would be a liquid if it wasn't for the high pressure. So that's kind of the rundown of the pressure and temperatures and the different phases of the layers of the Earth. And we'll take a 5-minute break, pause um, the video, mute everything on my end, And when we get back, we'll talk about the changing crust, which, you guessed it, is all about tectonics. Oops. Okay, so continuing to talk about chapter 8, moving on to the section called the changing crust. All right. So one way I hinted at that, we're going to focus on tectonics, but we're going to talk about some other aspects of the surface as well, including craters. So there are some evidence of cratering on Earth. And to put this in context, let's remember that Earth formed out of planetesimals, creating a molten, a hot ball of molten rock. As it cooled, it differentiated and caused layers in its interior. Unlike the moon, craters aren't visible on the surface because the crust is young. When we look at the moon, we're looking at almost 4 billion years of cratering history, much of it uninterrupted, some of it interrupted because of the lunar maria, the lava flows that we briefly introduced in the last lecture. But the vast majority just sort of just in this pristine state for billions of years, almost hard to reconcile a surface that remains sterile and unchanging for, you know, like I said, 4 billion years. Um, but we don't have to look far to see similar surfaces. Mars is much the same. And when people talk about water being on Mars, well, it's thought to be only have existed for the first 500 million years or so of the Martian planet after it finished its cooling and its differentiation. And that means that we've had just over 3 billion years of Mars with no water on its surface and basically changing, remaining in an unchanged state with craters never filling in, never eroding. But we're told here that Earth's crust is young. Why? Right? What keeps Earth's crust young? Okay. Well, lots of things. Okay. There's not one answer. You might think, oh, plate tectonics, because I mentioned it before. And that's a big factor. Plates are regularly being renewed. There's a huge amount of plates that are sort of recycled in a sense, in terms, especially if we look at the process between the mid-ocean ridges and where the ocean plates meet the continental plates. Subduction occurs, and that denser ocean plate is remelted just to create plate again somewhere else. But there's a lot more going on. We've got this the rift and subduction zone, which they separate from plate tectonics. Plate tectonics being just the overall crushing together and crunching, which would cause a certain amount of renewal. But this idea of rift and subduction is just, I mean, really directly like plate being destroyed and remelted. Um, Fault zones. So we have just, earthquakes occurring, causing, just shaking, right? That can, what is a crater, right? A crater is, susceptible to certainly a localized earthquake rather than a whole kind of global process, which are described by plate tectonics and rift and subduction zones. Um, Furthermore, volcanoes. Are volcanoes tied in with all of plate tectonics? Absolutely. If you look at where volcanoes are located, with some notable exceptions, they're often tied in with plate boundaries. Regardless, these are all separate phenomenon. And what's not even mentioned because of the focus on crust and all of this is the processes that are made possible because of our water cycle and our atmosphere, and both in tandem. So what I'm talking about is erosion, whether that's erosion caused by wind, erosion caused by glaciation, or erosion caused by precipitation. All of those are just always changing the crust. We've got, obviously our, river system, our oceans, all these things that make it so that things just don't last that long on the surface of Earth. You just see the recent history. Every so often, there's something where because of the location, maybe because of a location in the middle of a continental plate that is somewhat protected from surrounding phenomenon and just been eroding at a slow enough rate, you might be able to find a crater that is, a few 100 million years old. But that's about the limit. We don't have any visible craters that are even 1 billion years old. All of them have been erased. So, to get to one of the key aspects of this constant renewal of Earth's surface, we have the tectonic plates, and the crust is separated into those individual plates. You see them here. Plates are formed only if there is sufficient water in a planet's crust. So our current understanding of plate tectonics and the necessary ingredients for them is they require basically a liquid water on the surface. Okay, and also some, amount of water underneath the surface. And it's not just like for the plates to slide around, but just to create these like variable pressures to have the oceans pushing on plates in sections and not pushing in others, right? So we can think about this research paper studying the implications of water within Earth, okay? And how it can help us understand super Earths, which are a type of exoplanet that has been discovered around other stars. When we talk about tectonic plates, one of the processes that happens is subduction. All right. With subduction is when a plate moves, collide, or pushes under another plate. This causes the pushing up of mountains, the uplifting of mountains. All right. When plates grind together, they can open up holes for lava. Here we see an example of subduction with one plate sliding under another. In this case, an ocean plate, which generally have higher density, sliding underneath a continental plate. This red dot representing perhaps a earthquake event, and the melting oceanic plate then becoming the upwelling of magma, leading to lava coming out of a volcano. The volcano located a little bit inland, in other words, interior of the continental plate, and that creating a rim of volcanoes. And if we think about lines of volcanoes or the famous Ring of Fire, we see it located mostly on continental plates, a little bit from that boundary with an oceanic plate. Another type of plate interaction are the strike slip faults, like the San Andreas fault. This is where two plates slide together. Often these types of faults are associated with the smaller fragmented plates, the ones without big names, and that wouldn't show up on every global summary of plates. Because although we're seeing some very large plates like the North American plate here, we're not seeing some of the much smaller fragments of plates that can lead to strike slip fault interactions. Yet another plate interaction is the continental subduction. So one continental plate sliding under another. And think the heading here should not say strike slip, but just look at this one here, continental subduction. The plates move, in this case, colliding, pushing under each other, pushing up mountains, right? Same sort of thing, grinding together and opening up holes for lava. Very similar to the subduction that occurred with the oceanic plate and the continental plate. But sometimes this can lead to the largest mountains. If we look at, say, the mountain range, the Himalayas, that's a continental plate colliding with another continental plate and causing a continental subduction. All right, so I mentioned the importance of not just volcanoes and plates, excuse me, but also the processes of erosion, which collectively can be called erasure. So we have erosion caused by wind, water, and ice. Sculpt the rock created by geological activity. So geological activity is the processes we're just talking about. So with erosion, the motion of tectonic plates and lava flow from the Earth's interior, and those motions, the mountains, erase signs of craters from Earth's surface. So this is just summarizing what I said before. All right. So at least ancient craters. We can see the most recent ones, but the time frame is really limited. As I said, some of the oldest are just a few 100 million years. Obviously, a famous crater that has been looked for would be the crater that led to the crater associated with the impact that led to the extinction of the dinosaurs. Uh, Good reason to suspect that such an impact occurred due to sediment layers throughout the earth, and needing some explanation for such an extinction event, and not having another one. So a good confirmation would be to find the actual crater associated with it, and the best candidate is a crater kind of off the coast of the Yucatan in Mexico, but it's mostly under the ocean, and it's only visible with like satellite imagery, and it's hard to see exactly what is its age, when did it occur, because unlike on a surface that doesn't get changed like the moon's surface, where you can really exactly tell how old craters are often because of layering and being able to tell which crater fell on top of another one. Here, if we even have a crater, it's just one on its own because of its particularly large size and the huge amount of activity that it takes to erase it. And then, it even still gets erased because that event, extinction of the dinosaurs, was only some 65 million years ago. 65 million. We got a history of over 4 billion. So, we're really, really limited in which craters you can see. Case in point, look at this young crater, right? Dramatic crater, absolutely, right? Clear evidence of a crater, and it occurred about 50,000 years ago. It won't be around in 100 million years. It'll be completely erased by some combination of geological activity and erosion. Okay, here's the one I talked about, the Chicxulub crater. Okay, because it's named after the region, and so the Chicxulub event is the name given to the impact that thought to have created this crater and caused the climate change that led to the extinction of the dinosaurs. All right, 5 mile wide meteor. The crater is about 93 miles wide. Notice the difference. So that's often what you see is a 10 to 20 fold size difference between the size of the meat of the so of the asteroid, the rock that caused the impact, and the actual size of the crater. The crater is 10 to 12, excuse me, 10 to 20 times bigger. 11 is often used as kind of like a rule of thumb, but it depends on the material that was impacted. One thing that I just noticed that is a typo here is it says that this crater, the Chicxulub crater, formed 65 million years ago by a 5 mile wide meteor. The meteor was not 5 miles wide. The meteor is the name of the streak across the sky. If you wanted to say that a asteroid was 5 miles wide, that would be correct. Okay? You could call it a meteorite, but not really, because a meteorite is what's left over. So, you find a meteorite that's left from a collision, and that's just a fragment. It's the name given to the rock. That's why you have that meteorite ending. That ite is common for names of rocks, for mineral names of rocks. And so collectively, space rocks are meteorites. So really, it needs to be called either an asteroid, or a comet, or a astronomical body, if you wanted to be vague. But calling it a meteor is actually incorrect, and I imagine they just didn't catch that mistake. We got another one here, Crater Lake, formed 7,700 years ago by the collapse of a volcano. So this was not an impact from space. This is actually a volcanic event, and then just that had particularly unusual conditions where the volcano kind of collapsed in on itself. Okay, so I see. Yeah, that's why they point out, because it's like, wait, Crater Lake's not a crater, you know. So a good point. I didn't even think about that. We call it Crater Lake. Its name is misleading. Was not caused by an impact. I've gotten just so used to knowing that I didn't even think about how strange the name was. So I guess we should really call it Caldera Lake because it was like formed by the caldera, which is that sort of mouth of a volcano, and not just one that kind of like was left open but did particularly collapse. So that's how it has its well-known depth and size. Okay, so Earth's surface always getting renewed means that we don't have a certain way of looking at, the space history that we have on other worlds. But it's a good thing that Earth's surface is constantly getting renewed because, as far as we know, that's really closely tied in with what makes life so robust on this planet. Having these processes where continents are moving around, new species are getting exposed to each other, species are getting isolated and unisolated. There's always this exchange of nutrients and food webs seems to just really be a crucial aspect of what creates that global ecosystem and what we know of as this living world. So having all these changing processes, it seems to be of paramount importance. There could certainly be life in a more stagnant environment, but it most likely would not be as diverse. So now we're going to shift gears pretty significantly, but obviously still talking about Earth. And we're kind of going to zoom back into the center of Earth. We had gone up to the crust, but now we're going to consider a phenomenon that exists in space and well above the atmosphere and interacts with the solar system and the sun, but yet is created at the very center of Earth. And that is our magnetosphere. And our magnetosphere is the term given to the magnetic field. So and the magnetosphere is because of the shape of the magnetic field. It's, spherical, not a perfect sphere, but of course, permeates this whole spherical body. And its whole influence in 3 dimensions is the magnetosphere. But you could just call it Earth's magnetic field as well. So what is magnetism? Okay, well, obviously we have magnetic poles on this planet. That's not terribly common, okay? At least not on terrestrial planets. I'll just point this out, although we'll come back to it, that of the 4 terrestrial planets, Earth is the only one with a strong magnetic field and almost any magnetic field. Venus seems to have a very weak magnetic field. And I say seems because it's surprisingly hard to kind of get good measurements of it. But Earth really stands out. Mars has no magnetic field. Mercury has no magnetic field. Venus virtually no. So there you go, right? So really, really particular case. Although you'll see the Jovian planets all do have magnetic fields. So, it's not unheard of. It just seems to be less common, at least in our solar system, small sample size. But in our solar system with the 4 terrestrial planets, just us. Okay? So if you took a compass to Mars, it wouldn't do you any good. You wouldn't find a pole. But here you can. And that's because when you take a compass, which is essentially just a floating magnet with its north and south poles, it's going to line up. So what happens is the field lines that exist because of our global magnetic field connect the North Pole to the South Pole. And by definition, the field lines point towards the South Pole. So if I was to draw a field line, I would draw it coming from the North Pole, following the paths that are visualized by the iron filings, which are just a metal powder that's easily magnetized. And I would draw that field line like so. So it comes from the North Pole and it goes to the South Pole. Magnetic field lines don't have a beginning and end, so they actually will continue in the interior of the magnet. But if we're interested in the magnetic field that we can interact with on the surface of the world, we're talking about a magnetic field line like the one I just drew, because it's outside of the magnet, because the Earth itself is the magnet in this case. Okay? So there is our field lines. We removed the iron filings and then they would have traced them like I did, and then created these nice field lines. Okay. Here's the directions. So all the field lines, right, heading towards the South Pole away from the North Pole. And then furthermore, notice what's showing. It's actually so small, I missed it at first, but it's the compass, or it's a compass. And so if you look at this, this is it's kind of, it's small and a little like kind of washed out, but this is the needle of a compass. And so then notice that when you have a compass, it always has the white end. It's got the little center that the needle, will pivot around, and then it's got the north end, representing the north direction, and that it will swivel to line up with the ambient field, the external field, Earth's field. And then there's usually kind of a little shape to the red part of the compass that shows, that it's pointing in the north direction. That's what we're seeing in each case. Okay. So when we take a compass and we just, hold it flat, and you're going to see that needle of the compass line up with the direction of the field, which means, here's the kicker, it is pointing towards the South Pole, the South Magnetic Pole. You see it, right? I mean, look right here. Look at this compass. And it's like, you could think of the black line as being like the border, right? The actual, like, thing that you're holding. And so it's pointing towards the South Pole because, again, it's lined up with the field. If I'm over on this side of the magnet, right, I can clearly see that the north needle is pointing away from the north magnetic pole. So if I was really near the north magnetic pole of the Earth, my north direction would be pointing away from that. Okay. And that's always true, but it's more demonstratively true there. And then if I'm near Earth's magnetic south pole and I, pick up my compass and I hold it, I'll see the needle pointing towards the magnetic south. So you might see what I'm leading towards. Okay, but let me confirm. So under the North Geographic Pole, where Santa lives, is there a north or south magnetic pole? Which one is it? Let me know. Okay, Desmond says, okay, well, North Pole, it's north, right? Okay, does everyone agree? Under the North Geographic Pole, what type of magnetic pole is it? Angelina agrees. So let me remind you all that, well, gave away the answer. So let me tell you all that it's not. It's the South. And that's crazy, right? Well, it's because of this. Which way do they point, right? That's why I made a big deal by talking about the compasses. If I hold a compass, the needle on the compass, which itself is just a magnet floating in water, the north end of that floating magnet, which is the labeled as the north direction, will point towards the south pole of another magnet. I mean, you could just get like a strong magnet with a north and south pole and hold it near a compass, like compass you'd use for hiking, and then you would see that the compass would have its north needle pointing towards the south pole of the magnet that you're holding near the compass. So that means that when you're on Earth and you want to head in the direction that your compass says is north, and which is geographic north, that means it must be a magnetic south pole.
So it's like colliding into each other?
Yeah, they're
Okay,
attracted to each
okay.
other. They're
Okay, that
attracted.
makes
Yeah,
sense.
it's an opposites attract thing.
Okay, so I was
Yep.
thinking north because like colliding, then like crash, but I see what you're saying, opposite. Okay, that makes sense.
Yep. Yeah. Yep. Yep. North poles are attracted to south poles, and so that's what we see. And it's a fun fact. You can impress your friends and family with knowing that the South Pole, at least magnetic wise, is up north. And you might be like, well, then why didn't they just switch the names? But it'd be kind of weird, right? Because after all, it is the north end of the magnet that points, north. So it kind of makes sense to call that north. It's just attracted to its opposite. So yeah, so there you go. It would not be, I don't think it'd be satisfying the other way either. It's just the nature of how magnets work.
So is that technically energy? Like, so that would be kind of like the comparison to people?
Oh, with the opposites attract?
Like the whole, so it's an energy pool.
Yeah, it's the most direct comparison is with electrons and protons, where like because the
Okay.
negative electron is attracted to the positive proton. And yeah,
Negative.
it's the way that that it is in physics we say that everything is kind of like trying to go to a lower energy state, and that is
Mhm.
actually exactly what's happening here.
Okay.
Yeah, yeah. So yes, in general, here it is again. Right? Just a different pictorial representation of it. There's a North Geographic Pole up there, above Iceland, right? Depending which way you're looking, above the Nordic countries if you're looking from Europe, and you can see it's if you were look inside the planet where the magnetic field is being created, that would be a south pole. Okay, but we haven't addressed the issue of where the heck this magnetic poles, both of them and the whole field, where do they come from? Why do we have magnetic poles on this planet? Well, let's talk about it. So, the source of magnetism. Magnetism is always created by the motion of electric charges, no exceptions. Every magnetic field is created by a moving charge. You can create what's called an electromagnet by just having a coil of wire and running a current through it. So if you run a current with like, it connected to say a battery with the negative terminal powering this end of the wire here, and then so something like this. And if I had a battery and I had the negative end of the battery here, and I had the positive end here, and I just wired that battery to a piece of wire that was wrapped around, ideally some sort of like metal core because that helps strengthen and direct the magnetic field, but it could just be just empty. But if you then just let the current flow, so you let your current flow this way, then you're going to have I for current. Don't ask me why. Then you're going to get yourself a little electromagnet. And in the slides, you could follow this video to or this link to a YouTube video that explains how electromagnets work. So that's like a man-made magnet, and we've been taking advantage of how to make magnets and what we can do with them in circuits for last 100 years or so. But there's just magnets that just exist in nature too. Obviously, some rocks are magnetized, and you have permanent magnets that don't require electricity, like a fridge magnet. And so that's because you can have kind of this state build up where you can have everything lined up in at the atomic scale, and the actual motion, the moving charge is are going to be the orbiting electrons around individual atoms. And that's what can create a permanent magnet. And permanent magnets can be really strong. They all eventually can get demagnetized. Even your best permanent magnet, if you expose it to a stronger magnetic field or you heat it up and then expose it to, like a bunch of random direction magnetic fields, you'll demagnetize it. So, which just means that now all the electrons won't be moving essentially in tandem, right? They won't be all lined up neatly, which is what you would be able to see if you can zoom into the atomic level to a permanent magnet like a fridge magnet. But is that the mechanism for Earth? Is Earth just one big permanent magnet, just like a big rock that, that's solidified in such a way that everything's magnetized? Definitely not. For a couple of reasons. We know that the inside of Earth is super hot, so it wouldn't at all meet the conditions of a permanent magnet. Permanent magnets can't be liquids. They can't be bubbling, hot, molten, interiors of planets. So we know that Earth is not just is not a permanent magnet. That means that Earth literally is acting more like the electromagnet. It's as if there's a current somehow running through the inside of the planet. So how is that? Well, really, there's a few ingredients that make it possible. Well, one is that we have heat, obviously, got our molten, core and our super hot, yet solid inner core. And all that heat that's coming out of the interior of the planet causes convection. And convection is the rising and sinking of fluids. So that's where, hot air rises, cold air sinks is an example of convection. And that's happening with the magma inside of the planet as well. So as this is happening inside of the planet, that is creating a bunch of buildup of charge in the same way that when you rub your feet on the carpet on a dry day, you can build up a bunch of excess static electricity on your body. Kind of works on a dry day because on a wet day you immediately discharge it. But you can build up that excess static electricity by movement, by rubbing things together. So the convection of all this molten rock is building up a bunch of free electrons, essentially creating the ability of having a current. So we've got one necessary ingredient already taken care of, which is a bunch of available charge. And the available charge in the case of the electromagnet would be kind of coming from the battery itself, the chemical process that releases the charge, and the fact that we're talking about a pure metal, which are known for having what are called free electrons. But with a rock, you got to kind of have a better explanation, and the convection of the molten rock is the explanation. So what is also necessary, and let's see, I think I'll explain it here. What's also necessary is rotation. And the physics of that are going to be beyond the scope of the class. But there's a reason that our electromagnet was a coil of wire. It actually has to be that shape in some form or another. So you have to have a rotating current to create a magnetic field that goes north to south. Because notice that the field lines for the electromagnet ran perpendicular to the actual wires, each like rung of the wire coil. So the cylinder that was made by the coil of wire becomes the sort of the whole bar magnet itself with its two poles. Well, what creates the turning wire analogy for the Earth? Our own daily rotation. The fact that we spin on our axis every, about 24 hours, that's it. That is the key ingredient that, along with all that free charge, actually creates the magnetic field. So the fact that we have the spinning planet with all the free charge inside, where the Earth is just acting like a giant electromagnet. And it's got all kinds of interesting consequences. So if you look at those mid-ocean ridges that I mentioned, where the plates of the ocean spread apart, where they're getting renewed, because of course they're subducting under the continental plates and melting, so they're always getting renewed at these key, basically long ridges of small volcanoes. Well, that's always a steady generation of new rock that's just being created out of fresh magma, cooling, and becoming the ocean floor. And there's big mid-ocean ridges. I have to go all the way back to the slide that showed the map of all of the plate lines. But there's big ocean ridges basically down the middle of the Atlantic Ocean and down the middle of the Pacific Ocean. So along those mid-ocean ridge lines, like the mid-Atlantic ridge, because you have that steady creation of new ocean floor, you actually have this timeline of magnetic field direction. And when geologists study that timeline, they see that the polarity of Earth's magnetic field changes with fairly regular intervals. So our magnetic north and south pole switch every few 100,000 years, which is pretty regular if you think, that you got 10 sets of 100,000 years in a million years, right? And you got 1,000 million years in a billion years, and the planet's been around for, over four of those. So in the overall time span of the planet, there's been many, many times where the magnetic field has switched. It just switches like pretty regularly and literally just completely swaps, just spins all the way around. And just has to do with the kind of in the instability inherent in the system. It's kind of always constantly balanced, almost like balancing a pencil on your fingertip. You can keep doing it for a while, but eventually it's just gonna flip over. And that's the kind of physics that drives the magnetic field of any planet, including Earth. The fact that it's even stable for as long as it is pretty remarkable. But that's what this figure is showing is the polarity, which would, say like, whether north is geographic north or whether south, and I mean magnetic south, is geographic north. Because if, you know, they switched tomorrow, then we would then have agreement between what it means to be magnetic north and geographic north. Now, not saying that the switch would happen in a day, although current research suggests that the switch takes about 50 years. So it could happen within a human lifespan. And we're due for one pretty soon. But it's hard to say exactly when it'll happen. It's a range of thousands of years. All right. So kind of, and then on top of that, it moves around. So the exact location of either of the magnetic poles, in this case, highlighting the north magnetic pole, is moving. We can see back early measurements, which were less reliable and less frequent, but go back to 1590. So it kind of looping around throughout the 1700s, then tracing way down to kind of some northern Canada islands. And now, since 1831 and more recently 1904, and throughout the 20th century, steadily moving towards almost due, north, right? The actual geographic North Pole is getting closer and closer to be the current location of the magnetic South Pole. And so, we've had this kind of gradual movement. And this wiggling around isn't the same as the switching. It's just, showing that this is an unstable system. Now, I promised that I'd mention the magnetic field in the context of space because it's made in the interior, but its effects are on the surface, obviously, you know, because hey, we can use a compass to find it. And animals use it, right? Birds use it for navigation, fish, many animals have evolved ways to sense the magnetic field and use it. Humans don't seem to detect it directly, but it extends well beyond the surface, well beyond the atmosphere. By the way, Earth's atmosphere is only about 100 kilometers thick. It's just a thin layer. But if you go way up into space, even past, the orbits of most satellites, you would reach the end of the influence of Earth's magnetic field, but it's quite a large region. The very edge of our where the magnetic field becomes too weak to really make a difference is called the magnetopause. So this is the edge of the influence of Earth's magnetic field. So it's just and the whole region within the magnetopause is the magnetosphere, the zone around the Earth where the Earth's magnetic field dominates. And dominates as compared to what? Well, other electromagnetic influences. One of the biggest ones being the solar wind. The sun constantly releases light, yes, but also it constantly releases another just steady flow. And that is charged particles, mostly just plain old electrons. They're just streaming out from the sun basically in the same direction that sunlight does, just outwards in all directions. And we call that phenomenon the solar wind. And it's just a bunch of streaming electrons. And we actually can see a effect, an interaction between the solar wind, which is not a wind at all. It's just called the solar wind. It doesn't, it it's not like an atmospheric wind, right? Because of course space is mostly a vacuum. So it's not like a fluid flow. It's just a bunch of individual tiny little electrons. So, it's more accurately shown, right? Is all these little white lines. So it's like a bombardment of particles. Well, but that interaction that I mentioned, all right, is going to be the aurora. Because when the solar wind interacts with Earth's magnetic field, it causes the electrons from, within the solar wind, from the sun, to spiral inwards on Earth's magnetic field lines and therefore approach either of the poles. Well, where are the poles? Well, they're near our rotational poles, north and south, which means that at the extreme latitudes, such as, positive 70 to positive 90 north and negative 70 to negative 90. So this is, the southern latitudes. Well, you're going to have the ability to see the auroras, either the aurora borealis or the aurora australis. And the good way to describe that is particles being funneled along the magnetic field lines until they reach the atmosphere and excite molecules in the air. Because when we see the glowing northern lights, we're seeing the interaction of the funneled electrons, the electrons that compose the solar wind. Of course, it's a small portion of it, just the ones that happen to be trapped by our field lines. Most of by the way, the solar wind just gets redirected. And I'll just point out before I say any more about the auroras, is that that's a good aspect of our magnetic field because it helps protect our atmosphere. If our atmosphere is constantly exposed to the solar wind, it would just gradually dissipate because then all the energy from the solar wind would get transmitted to the molecules in the atmosphere. That would cause the molecules to excite to velocities that are greater than the gravitational escape velocity in small proportion, but over time, we would just lose our atmosphere. We just gradually sort of boil away in a sense, but over a very large time scale. So being able to hold on to our atmosphere and have our nitrogen rich and oxygen crucially, composed atmosphere would not be possible without our strong magnetic field, our planet's strong magnetic field. But let's look at that solar wind. So to come in, representing a bunch of little green dots here. Each one is like our, electron. There are some protons in the solar wind, but mostly electrons. And then it comes in, so it starts hitting the magnetic field, and then immediately gets affected by it. So now all these charged particles are getting redirected by the magnetic field, because that's, by the way, one thing that magnetic fields do. They affect electric fields, and they also affect moving charged particles or currents. And so that's what's happening here. This is a electromagnetic interaction, charge interacting with magnetism. Okay, so then this is that funneling. The actual path is helical. So the electrons would be spiraling down individual field lines, but the field lines can have variable directions, and but in general they would spiral downwards. So you're not going to see any of the electrons reach the equatorial latitudes because there's no easy path for them to take. They can't just jump across, right? They have to follow the field lines. And so as those electrons follow the field lines, they approach the North and South Pole. And as they do so, they come close enough to the surface that they actually enter the atmosphere. And that's when we start seeing those energy interactions, the same ones that would destroy the atmosphere if we didn't have a field, a magnetic field. If we just lost our magnetic field, all of a sudden there'd be northern lights everywhere every night, and no life within, I don't know, a few thousand years at most. So, but in this case, right, we have we have them coming down and just reaching those northern latitudes. And does that like make, for harmful radiation? Not really, because it's not that the northern lights and the release of their energy itself isn't harmful. It was just the way that it could cause the atmosphere to gradually disappear over time. That's the harmful part. But since it's localized, we're not losing a significant amount of our atmosphere. This is what they look like, of course, from the surface, from space. Okay. So we'll have to put a pin in it for that for today. We'll call this our stopping point because we got 3 minutes left, but we're at a good junction. So basically, I just got to talk about climate change. So I'll make sure to think about how I can summarize it quickly and hopefully just wrap it up next time. But we will have a Canvas quiz for this material, and I'll try to remember to post it this afternoon, although it's not the top of my to-do list. But when I post it, I'll always make sure it'll be due a day after I post it, so we have at least a day and a half. And other than that, as I said, we'll almost certainly have a Chapter 9 quiz on our Thursday meeting. Should be Zoom. Okay, well, I think that's it for class business. Let me stop my recording. So I could have stopped before that.